Assalamu alaikum wa rahmatullah. So we're here with tutorial number 4 for our data structures course ES210, and today we're going to have a look at a few examples before we continue with the tutorial. So I'm going to start with this very simple example. Let's say this is given to you, assuming that there is some program whose total number of operations turn out to be something like this. So 2n plus 100 log n. So we know that using the big O notation, we're going to look at uh, the highest order term. So in this equation, the highest order term is 2n, and 100 log n is a smaller term. So we have to prove that this is big O of n. Now to do that, what we can do is we can find the value of c and n naught such that we can prove this value is larger than this. So if you're able to prove this value Cn is larger than my equation, then I can say that yeah, this condition holds and that this equation is O of n. So using simple algebra, we try to solve it for n. So you can see 100 log n, we can move to n on the right side, and then we can come up with this, where n times c minus 2 divided by log of n is bigger than or equal to 100. Now since we just want to justify this, we can substitute the values of c and n naught. So in this scenario, if I put c to be 1, if I get c equals 3, I can get 3 minus 2 equals 1. So my equation now becomes 100 less than or equal to n divided by a log of n. Now again, we have to solve for n. So find a value for n naught such that this condition holds. Now log of n, we have a simple property because this is log base 2. So we know that log base 2 of 1 is 0, log base 2 of 2 is 1, log base 2 of 4 equals 2, log base 2 of 8 equals 3, and so on until log of 1024 gives me 10. So if I substitute n naught for a value, let's say 1024, let's say n naught is 1024, so if I substitute this value in there, I get 102.4, which is definitely bigger than 100. So I can say that using value c equals 3 and n naught equals 102.4, 102, I can justify that this equation holds. So another example. So here's another example. Let's see how this works. Let's say there's another equation which is 2n cubed plus 10n log n plus 5. So the big O notation for this equation is, again, we have to look at the highest order term, which is 2n cubed in this case. So if you remove the coefficient, we get n cubed. So we can say big O notation for this is O of n cubed. Now if somebody says justify that this is O of n cubed, we can simply put an equation like this, where 2n cubed plus 10n log n plus 5 is less than or equal to cn cubed. C is some constant. So try to solve it for n. So 5 is less than c minus 2 into n cubed minus 10n log n. So if I put c equals 1, if I choose c equals 1, I can get 1 over here, which means I can solve the equation like this. So 5 is less than or equal to n cubed minus 10n log n. Now since again we have log n here, this means we need to be careful when we're choosing the value of n. So let's say n is 2, n naught is 2. So if you substitute the values in there, we get to the power 3, which is 8, minus 10 times log 10 times n, which is 2, multiplied by log of n. Log of 2 is 1. So this will not work. Let's choose another n. Let's say we have 4. So 4 cubed minus 10 times 4 times 2. 4 cubed is 16 times 4, which is 64. So this is not holding because this will go above, this will be 80. It's going to give me a negative value. Let's say n naught equals 8. So 8 cubed is 512 minus 10 times 8 times log of 8, which is 3. So this holds, the value is greater than 5. So I can say that I can satisfy this equation with c equals 3 and n naught equals 8 to prove this. So let's look at another example. Here we have an equation 5n squared plus 3n log n plus 2n plus 5. So just by looking at the equation, you can say, look at for the higher order term, which is 5n squared. I can say this is O of n squared. So if I want to justify that, again do a simple algebra. This is less than or equal to cn squared. I can solve it for n. So 5 less than or equal to c minus 5 n squared minus 3n log n minus 2n. So choose cn and not to justify. So again, you are at total liberty to find the value of c and n naught. So I'm going to pick c equals 10 and n naught equals 2. So using these values, if I substitute in that equation, I get 20 minus 10, which holds. So I can say the value of c equals 10 and n naught equals 2 works to solve this equation. So having learned about justifying the big O notation for a program, let's get back to our tutorial and see if we can do some of these exercises. So my first question is, the number of operations executed by some algorithm A and B is 8n log n and 2n squared respectively. Determine n naught such that A is better than B for n larger than or equal to n naught. So you have to come up with a value for n naught so that you can justify that algorithm A runs in more time compared to algorithm B. So we know that 8n log n is a lower order term compared to 2n squared. Nevertheless, let's see if we can find a value for n naught, and if you substitute in there, you can justify that this runs slower than that. So here's the solution for the first question. For algorithm A, the number of operations is 8n log n. Of course, this is given to us. And for B is 2n squared. So we have to find the n so that A performs better than B. We know that O of n squared is a higher order function compared to O of n log n. So we have to find a value of n so that we can justify that in this scenario A is bigger than B. So we rely on the mathematical fact that a log of n is less than or equal to n for all positive n. So using this logic, I can say the 8n log n, because log n is definitely less than or equal to n for any n larger than 1, I can say I can substitute log of n with n naught. So roughly it's going to give me 8 into n squared. B on the other hand is 2n squared. So if you're just comparing the order terms, they're the same. The only difference is the coefficients now. So I can justify that 8n squared runs slower compared to 2n squared. In other words, A is larger than B. So let's look at the second question. The number of operations executed by algorithm A and B is 40n squared and 2n cubed respectively. So determine n naught such that A is better than B for some value n such that n is larger than n naught. Now when I say A is better than B, this means number of operations for A should be less than number of operations for B. In other words, we say this runs faster compared to this, the other algorithm. So let's see how to do that. Now I want to say that A's time is less than B. Here's my A, here's my B. Simply go ahead and substitute the values. So let's say n equals 1. So if I put n in there, It's not less, it's in fact larger. So that does not hold. If I put n equals 2, I get 80 for A, and B is 16. So it does not work. So you keep substituting values in there until you reach 20. When I reach 20, I notice that number of operations becomes equal, 16,000 and 16,000. For any larger than 20, a value of n, I notice that now the algorithm B becomes slower compared to the first algorithm. So I can say that the value of n naught over here is 21 or larger. If the value of n is 21 or larger, I can say that safely A runs faster compared to B. So next question, order the following functions by their asymptotic growth rate. So of course the slowest function is always exponential, which is 2 to the power n. Slower than this is n cubed, and we also have 2 to the power log of n. Now if n is very large, let's say I pick 1 billion, around 1 billion. So log of 1 billion will give me approximately 30 to the power 30. And here I have n cubed. So billion cube, I suppose, would be larger than 2 log n. So this is a bit controversial. You have to give it a bound, upper and lower bound, so you can determine which is slower, which is faster. So the way we are looking at it, in manageable n size. So the slowest is 2n cubed, to the power n. Then we have n cubed. Then we have 2 log n. Alright. Next we have n squared. So big O notation for n for this function would be O of n squared. Then we have 4n log n plus 2n. So big O notation for this would be n log n. Then we have n log n. So again, big O notation would be the same, n log n. Then we have 3n plus 100 log n. Okay, because n, of course, is slower than or smaller than n log n. Next we have 4n. And finally we have to the power 10, which is a constant. Next we have question number 5. This question we've given some code. What you have to do is you have to go and find the number of primitive and non-primitive operations in the code. So we've done this thing in the class. You have to find the number of operations for every line, and at the end you have to add up all of the number of operations on all the lines in the program. So let's look at this simple program. So I have a method called example1. Of course we do not consider this because it would be called by the other method, whoever is going to call this method. In line number 3 we have 2 operations, which is integer n equals array length. So we go and find array length. This is one operation, and we declare a new integer and store this value in there. This is another operation, so that's 2 operations, and we say total equals 0. Somehow it's declared somewhere else, so we're simply saying we're initializing the value, so that's a constant type. So 2 plus 1 constant operations. Line number 4 is a loop. So we have integer j is 0, j is less than n, j plus plus. So j is 0, this is going to work only once. Then we have j is less than n, which is the condition in the loop. This condition runs n plus 1 times. And then we have j plus plus, which runs n times. Next, we have total plus equals array of j. So fetching the value for array of j, this is one operation, and you summing this thing up and storing this in total, that's one operation. So altogether this is 2 operations. But since this is inside the loop, so you have to multiply it with number of times the loop is running, which is n. So we get 2n. Line number 6 is return total, which is one simple operation, one primitive operation. So altogether total time is 4n plus 6. So if I want to find the big O notation for this, that will be O of n. So let's look at the next example, example 2. We have some code over here. Let's see how do we find time for it. So number of operations, integer n equals array.length. Again, this is going to go and fetch the value of the size of the array. We declare value the integer n and we store the value in there. That's 2 operations. And total equals 0. So there's 3 operations on line number 11. Line number 12, we have a loop here. So integer j equals 0, simple initialization, 1 operation. J is less than n. Now we have to look at it, how many times the loop is running. Now the increment value is not +1, it's incrementing by 2, which means that, let's say for value 0, and then 2, and then 4, and then 6, and then 8. So we're just looking at the even number of operations, not the odd. So this won't be n, this would be half of n. And of course, the last time you're going to come and look at the value, so the condition becomes true. So this is going to be 1 plus n divided by 2, and half of n plus 1. And how often are you going to implement this? J equals j plus 2. Again, this is going to be half of n. Right. Line number 13 is total equals total plus array of j. So this would be simpler. This is 2 operations. This is inside the loop, so 2 times n divided by 2. And the last line is total, which is 1 primitive operation. So if you add up all the things, you're going to get 2n, because n plus n divided by 2 plus n divided by 2 is n. And same thing over here. So we have 2n and 6 constant operations, 2n plus 6. So if I want to find the big O notation for this, the highest order term is n, so I'm going to say O of n. Next we have example number 3. This looks interesting because there's a couple of loops in there. Let's see how this is going to work. So line number 19, integer n equals array length and total. So again we have 3 operations here, 2 or 3. It should be 3 operations. Line number 20, we have a loop for integer j equals 0, j is less than n, j plus plus. So increment value is just 1. This means the loop is running n times. So j equals 0 is 1 operation. The loop runs n plus 1 times, or n times. This condition runs n plus 1 times. Next we have line number 21, a loop inside another loop. So this operation is going to run 1 time. The loop is incrementing by 1, and it's running for k is less than or equal to j. So in the worst case scenario, this is going to run n times. Let's say the value of, we approach over here where j is n minus 1. So this loop is going to start from 0 all the way until less than or equal to n minus 1, and you're running n times. So, and the last time is going to check this value when this becomes equal to n, so the loop would stop. So this is why I can safely say n plus 1 is the number of times this is going to work. And k plus plus is a simple increment which is running n times. So all of this is since inside the upper loop, which is controlled by j, which is running n times. So I'm going to multiply all of this time with n. So what I get over here is 2n plus 2n squared. Next, line number 22. So this is inside both of these loops. So total equals total plus array of j. Let's say this is 2 operations. So I'm going to say 2 multiplied by, this loop was running n times, and this loop was also running n times in the worst case scenario. So this is 2n squared. And of course return total is outside the loops. It's a simple primitive operation. So if I add up everything, I get 4n squared plus 4n plus 5. So highest order term is n squared. I can say this program runs in O of n squared time. Let's look at the next example, example 4. So we have integer n equals array length. We have a variable prefix equals 0 and total equals 0. So these are 2 variables to initializations. You go and fetch in value for array. This is 3, and integer n, that's 4. So this is 4 operations. There's 4 operations on line number 28. Next we look at line number 29, which is a loop. For integer j is 0, j is less than n, j plus plus. So simply this loop is running n plus 1 times. This condition is running n plus 1 times. The loop runs n times. Okay, this condition, this statement is inside the loop. So prefix plus equals array of j. This is 2 operations. Since the loop is running n times, so I can say this line runs 2n times. Same thing here, 2n times. And the return is outside the loop. So this is 1 operation. So if I add up everything, I can say I get 6n plus 7. Since we have to find the O, the big O notation, the highest order term is n. So this program runs in O of n times. So let's look at the last one, example 5. This is a bit longer code. Let's see if we can do that. So we're receiving 2 parameters, which are references to 2 arrays. Again, we do not consider that because this is just given. We're not initializing that. Now, line number 38. So integer n equals first of length and count equals 0. So it's 1 operation, 2 operations, and initialization of n is 3 operations. So next we have the loops. Let's look at the first loop. For integer I is 0, I is less than n, I plus plus. Now the loop is running n times. So it's simple enough. I can say 1 plus n plus 1. Condition goes n plus 1 times, and this runs n times. Next line is inside the first loop. So since this is running n times and this is 1 operation, we say it will take n times 1, which is n time. Next is line number 41, which is another loop. This time the loop has integer j initialized to 0, j is less than n, j plus plus. So if I'm just looking at this loop, this is running 1 time, this is running n plus 1 time, this is running n times. Now all of this is inside the upper loop, who's taking n time, so I can safely multiply everything with n. You can see line number 41, n times this, which is giving me n times 2n plus 2. Next, line number 42. So line number 42 is for integer k is 0, k is less than or equal to j, k plus plus. So because of the equal sign, and since this is j, it's not controlled by a value such as 0 or n, and j could be changing. So first time when I run this loop, let's say n is 1, the value of n is value of j is 1. So when I come over here, k is less than or equal to 1. This means this loop runs 2 times. For k is 0, for k is 1. When j becomes 2, we run the loop for 0, 1, and 2, and continue. So it's growing. The first time you get in here, you only check for 0 and 1, or 0 only, and then 0 and 1, and then 0, 1, 2, 0, 1, 2, 3. So this keeps growing until you reach the last value. So the last value over here would be n minus 1. So we run this loop, the k loop, from 0 until less than equal to n minus 1. Yeah, and in other words, n times. So the time for this is variable, and in the beginning it's 0, and then 1, and then 2, and then 3, all the way until the last time is going to be n minus 1. So this can be quantified in a better way, but since we're just looking at the worst case scenario, so the worst case scenario, this loop runs n times. So for line number 42, n multiplied by 2n plus 2, which is the time taken by the previous loop, multiply this by the time taken by this loop. So I get something like this, which is equal to 2n cubed plus 8n squared plus 6n. Line number 3 is inside this third loop. So total equals total plus first of k. This is 2 operations. So simply go look at the time for line number 2, multiply this by 2. So this was the time it took for line number 2, multiply that by 2. Next we have line number 44. Notice this is outside these two loops, but still inside the first loop, which is controlled by I. So here, if get the value, fetch the value, this is one operation, equal to total, which is defined locally. So this is two operations. So I can say n times 2, because the first loop is running n times, and there's two operations. Now inside this, we have count plus plus. So if this condition holds, if this is true, we increment count. If this is not true, we do not increment count. We skip that line. So in the worst case scenario, let's say this is true for all the cases. So this is going to run for the equal number of times, which is inside the first loop running n times. This is why what I do is I simply multiply this number of operation, count plus plus is 1, multiply this by n. And line number 46 is return count, which is a primitive value. So if I add up everything, I get roughly or exactly 6n cubed plus 26n squared plus 26n plus 6. Now if I want to find a big O notation for this, again look for the highest order term, which is n cubed. So I can say this program runs in O of n cubed time. Thank you for listening. This is the end of the tutorial.